Consider the energetics of this circuit over here, where we have an EMF source like a battery, some resistor, and some inductor, and that we have some current flowing through the circuit because of the EMF. And so Kirchhoff's loop law says if we start down here, we gain the EMF, we lose IR because we're going along with the circuit, and then we gain L di dt. At the moment, we're assuming di dt is positive, and so we know that the EMF would point backward this way. All right, this is assuming, here we're assuming di dt is positive. So the current is getting stronger this way, so the back EMF points this way. We're traversing that EMF the wrong way, quote unquote, and so we gain the potential back. Let's multiply through by the value of the current because, we can do anything we want, so why not that? Oh, there we go. This, of course, should be the EMF. And we have the EMF times I equals I squared R plus the inductance times I times di dt. And we know that the EMF times I is the power that's being delivered by the battery. That's the work being done per unit time to lift charges through that potential. And of course, I squared R is the power being radiated out as heat by the resistor. We've had that for a while. So then we're left with this term, and I'm going to hypothesize for the moment that this is power that's being stored in the inductor or something. There's power going into the inductor. By energy conservation, all the power delivered by the battery has to go somewhere. Some of it is radiated away by the resistor. The leftover must be being stored in the inductor, specifically in the magnetic field that's threading through it. So we can say that the rate of change of magnetic energy per unit time is the inductance times the current times the IDT. So we integrate dUB, right? We'll cross multiply by dt, and these go away. Now we have dUB is Li di. Integrate both sides. The integral of a pure differential like dUB is just UB. And the integral on the other side, well, L is a constant, doesn't depend on the current. So bring outside, I have integral I di, that's 1/2 I squared. So we end up at the end with the important result that the energy stored in an inductor in its magnetic field is 1/2 times the inductance times the current squared. Notice how similar this is to the energy that's stored in the electric field of a capacitor, which was 1/2 Q squared over C. And we're going to see multiple times where our definition of capacitance is inconvenient because the C ends up on the wrong side of every dividing bar. And it would have been nicer if we had defined instead that instead of saying Q equals CV, had we said the voltage on some capacitor that's holding some amount of charge is like this. Call something different here. Had we done this, then we would have had a lot of nicenesses because it would, for instance, add the way that resistors add and so on. But we didn't, so we're kind of stuck. Consider a solenoid of length L and cross-sectional A. We can investigate the unit energy per unit volume of it, the energy density, using that result. UB is going to be, little ub, which is the energy density, is capital UB over V, the energy we have divided by the volume in which it is stored. That, of course, would be the energy we have divided by A times L. But the energy we have, we just found, was 1/2 Li squared. For a solenoid, we know that the inductance is mu naught times the turn density squared times the area times the length. And then we have 2A, we have this 2 and the AL, and I squared. Notice that the AL goes away, the dimensionality of it goes away. We're left with mu naught n squared I squared. I multiply by mu naught over mu naught, so I can transform it into this weird construction because this thing in parentheses is the magnetic field of the solenoid. So I end up getting that the energy density inside the solenoid is 1/2 its magnetic field strength squared over mu naught. And just like before, although we derive this for the solenoid in the case of constant field, it can be shown that it's true anywhere there's a magnetic field at all. If there's a magnetic field in space with strength B, then there's an energy density there, joules per cubic meter of 1/2 B squared over mu naught. Again, this looks very similar to the energy density in an electric field, which we found was mu E times, was 1/2 epsilon naught times E squared. You'll notice that it's because of the way we define our constants, mu naught and epsilon naught tend to appear in opposite sides of the solidus. Don't worry about it, it's not a big deal, but it's interesting to note. And we might also say there's sort of an interesting result that comes out when you consider that the units of UB, which are joules per cubic meter, are the same as a Newton meter per cubic meter, of course, that's what joule is, which is a Newton per meter square, which is the unit of pressure. So it also says that fields, magnetic or electric fields, exert pressures for their existence. They kind of push each other away and push things away inside of them. They're like, again, this is kind of modeled on the idea of, that we always go back to. It looks kind of fluidic. Don't read a lot into that, but it's kind of interesting. And in things like solar magnetohydrodynamics, it's kind of interesting to see that you can actually model the flow of the magnetic fields themselves as if they were acting to their own pressures, that where they're pinched together, there's a lot of pressure so that they want to fly apart.